Commander, let's light the sky. Training sharper drone pilots, learning how to fly. Mission ready mindset, safety leading every plan. Skills that build confidence from takeoff through the scan. Tune in at Sky Commander, come join the crew today. Learning smart, fly with purpose, level up your way. We see more, no sooner, that's the edge we're here to spread. See above, go beyond, get ahead.
Okay, let's get started.
So, starting off today, what do you think is the single most expensive mistake you could make with a high-end, multi-thousand-dollar LiDAR setup?
Well, I mean, if you're looking at a drone carrying, $100,000 of scanning equipment, most people would probably guess it's a catastrophic hardware failure.
Right, like a crash.
Exactly. Crashing the aircraft into a transmission tower or a battery failing mid-flight and just dropping the sensor straight onto the concrete.
Yeah, see, that is exactly where my mind went when I first opened the sources for today's deep dive. But according to the materials we're looking at, the answer has absolutely nothing to do with crashing the aircraft.
It doesn't.
No. The most expensive mistake is actually a psychological one. It's the belief that the job is done just because the aircraft landed safely.
Oh, that false sense of security.
Exactly. You take the SD card out, you load up this massive file full of millions of colored points, and you feel this overwhelming sense of comfort. You look at the screen and think, we captured reality. But the reality underneath that point cloud might be, well, it could be structurally compromised, mathematically inaccurate, and just entirely useless for the client.
The paradigm shift our sources are trying to force here is profound. We are tracking a fundamental shift in professional identity within the spatial data industry right now.
Yeah, a shift from what to what, exactly?
It's the transition from thinking like a pilot to thinking like an operator. Because a pilot is someone who, just executes flight routes.
Right, they just fly the lines.
Yeah, they look at a screen, draw a polygon over a field, and basically tell the drone to fill that polygon with a lawnmower pattern. But an operator does something entirely different. An operator engineers evidence.
Engineers evidence. Man, let's really unpack that phrase because it frames everything we're going to talk about today.
It's the core of the whole thing.
Right. The core philosophy here is that the point cloud, that giant, beautiful 3D model that looks like a digital twin of the world, is not the final product.
Not at all. It's merely a consequence.
A consequence of the geometric choices you made in the air. The real product, the thing the engineering firm or the utility company is actually buying, is the structural strength of the evidence inside that file.
And if we look at the mechanics of that strength, a pilot flies to maximize battery life, right? Or to cover acreage as quickly as possible.
Efficiency over quality.
Exactly. But an operator designs the flight geometry so the resulting data comes back mathematically robust. They want data that is easier for the classification algorithms to understand, easier for the analyst to process, and ultimately, and this is the big one, bulletproof, when it has to be defended in a design meeting or even a court of law.
So to map out where we are heading today for you listening, we're going to explore why generating better data doesn't just mean producing a bigger file size.
That's a huge misconception.
It really is. We're going to look at how professional operators plan backwards from the very specific mathematical needs of the client. And we'll detail the absolute domino effect of tweaking your flight settings.
Because changing just one knob changes everything.
Exactly. Changing your altitude secretly alters the physics of the entire capture. We're also going to look at how the physical world, specifically complex terrain and vegetation, actively works to sabotage those settings mid-flight.
Oh, nature is the ultimate enemy of LiDAR.
Definitely. And finally, we will ground all of this in the strict legal realities of operating these systems in the national airspace of both the U.S. and Canada. Because physics doesn't care about your project deadlines, and aviation authorities certainly don't care how expensive your payload is.
To understand how to engineer that evidence effectively, the first hurdle is dismantling what the sources consider the biggest prevailing myth in the industry today.
The worship of density.
Yes. We have to stop worshiping raw point density.
The vanity metric. Our sources specifically refer to this as the trap of ego density versus useful density. And reading through this, I can see exactly why so many newcomers get derailed by this.
It's super tempting.
Right. You look at the spec sheet for your brand new LiDAR sensor, you see the pulse repetition rate, the PRR saying it can fire 2 million pulses per second, and you think the goal is just to blanket the Earth in light.
And you come back to the office with a file so massive it crashes your workstation.
Yeah. And you view that giant file size as proof of a job well done. But a giant file full of points can still be incredibly fragile, right?
It absolutely can be. A massive cloud is structurally want if the density is only high on the easy, highly reflective surfaces, like, say, a flat, freshly paved parking lot.
But sparse where it actually matters.
Right. If it's sparse at the bottom of a V-ditch hidden under scrub brush, it's useless. The ASPRS, the American Society for Photogrammetry and Remote Sensing, provides a vital mathematical distinction here that every operator needs to understand. Increasing the density of the point cloud does not improve the individual measurement accuracy of the sensor itself.
Let's hold on that point for a second and really break down the mechanics. If I fire the laser twice as fast, giving me double the points, why aren't those points more accurate?
Because the accuracy of a single point is governed by the internal hardware cascade of the system, not the volume of points.
Like the IMU and the GPS?
Exactly. When a LiDAR sensor fires a pulse of light, it calculates the time of flight, how long the light took to bounce off the ground and return. But to turn that timing into a 3D coordinate on Earth, it relies entirely on the GNSS receiver to know exactly where the drone is in the sky, and the IMU, the inertial measurement unit, to know exactly how the drone is tilted.
And it's measuring that tilt constantly,
Yeah.
right?
Hundreds of times per second, measuring pitch, roll, and yaw. The baseline accuracy of your data is locked into the quality of that IMU and GNSS trajectory. Firing the laser 2 million times a second instead of 500,000 times just gives you more points that share that exact same baseline error.
Ah, so you haven't made the sensor sharper? You just asked it to sample the ground more frequently.
Precisely.
So if it doesn't make the individual laser hits any more precise, what is the actual tangible benefit of having denser data?
Denser data improves the quality of the derived surface by shortening the interpolation distance.
Interpolation. That's basically the software's guesswork, right?
Yeah.
What does that actually look like when the software is trying to build a model?
Well, when you hand a point cloud over to civil engineering software to create a bare Earth model, the software builds what's called a TIN, a triangulated irregular network.
A web of triangles.
Yeah, it essentially draws a web of triangles connecting your ground points to create a continuous surface. Interpolation is simply the math the software uses to guess what the ground looks like between the points you actually measured.
So if there's a gap, it just draws a straight line across it.
Right. If your points are spaced 3 feet apart, the software draws a flat triangle across that 3-foot gap. If there is a small rut, a curb, or a protruding rock sitting inside that gap, the software completely misses it. It assumes the world is a series of flat planes.
Oh, wow. So by increasing the useful density in that specific area, you shorten the gap between the points.
You force the triangles to be smaller. You are requiring the software to infer less and observe more of the microtopography.
There is a brilliant analogy in the source text that crystallizes this. They compare the raw output of the sensor to a fire hose and a targeted mission plan to a garden hose.
I love that analogy.
Yeah, if your ultimate goal is to water a very specific bed of delicate roses, a fire hose is certainly going to spray a massive volume of water. It feels powerful.
But that doesn't mean it's watering the right flower bed.
Exactly. In fact, that sheer undirected volume is probably just washing away the topsoil you actually need. But wait, let me stop you there and play the role of the eager new operator. I have a sensor that costs more than my car, and I have an absolute beast of a computer back at the office. Why can't I just fly high, fly fast, crank the PRR up to maximum, and let a smart software algorithm sort out the sheer volume of data? I mean, software is practically magic these days. Brute force should work.
The brute force approach fails because of the physics of how the light interacts with the environment. And PRR is frequently misunderstood in this context.
How so?
Think of the pulse repetition rate simply as the speed at which the sensor is asking the ground a question. Where are you? Where are you? Where are you?
Okay, makes sense.
But if you were asking those millions of questions from the wrong geometric angle, or if your flight lines leave huge gaps in the physical overlap, the answers you get back are useless.
The speed doesn't fix a bad angle.
No. A high PRR will not magically bend light around a building to see the sidewalk if you flew at the wrong angle. And it won't save you if you fly so fast that those 2 million points are stretched out into thin ribbons along your flight path, leaving massive interpolation gaps between the laser's physical sweeps.
So the sensor is asking the question, but the flight geometry determines if the ground is even capable of answering.
Precisely. The geometry dictates the capability. And this brings us to the 3 specific ways a point cloud must support a deliverable.
What's the first one?
First, it has to physically shape the feature. You need enough points hitting the target to define its actual geometry, whether that's the sharp edge of a retaining wall or the curve of a pipe.
Right. And the second?
Second, it has to provide structural consistency so the classification algorithms can function. If the density wildly fluctuates, the algorithm gets confused and starts misclassifying ground as vegetation.
Which ruins the model.
Yep. And third, it builds client confidence. You want the lead engineer on the project to be able to zoom all the way in on the most complex, heavily vegetated, steepest part of the site, look at the underlying data structure, and not feel nervous about designing a $1 million drainage system based on your surface.
The sources summarize this perfectly. Mission planning is ultimately an honesty decision.
It really is.
Yeah, a weak plan forces the software to lie, to interpolate, to smooth over, to guess at the terrain. A strong plan actually measures the truth. And the choices you make in the field are passed directly downstream. If you cut corners in the air to save 5 minutes of battery life, you are basically injecting mathematical ambiguity straight into the final model.
Which is why the concept of planning backwards is the foundation of an operator's mindset. If raw, undirected density is not the goal, you cannot plan a mission by just looking at the drone's capabilities.
You have to start at the end.
You have to start at the absolute end of the pipeline with the specific mathematical deliverable the client is purchasing.
Because a digital terrain model for a floodplain, a utility inspection for a power line, and a volumetric measurement for a gravel stockpile do not require the same kind of point cloud.
Treating them as if they do is the fastest way to identify an amateur in this industry. Let's dig into the specific mechanics of these deliverables. Take terrain models, for instance.
Okay, let's look at those.
When a client orders a bare earth model, the entire value of the project lives exclusively in the points that are classified as ground.
So the total point density is irrelevant.
Completely irrelevant. The only metric that matters is the ground density after the classification algorithms have done their job.
Right, because if I'm mapping a field covered in waist-high dense grass, I might have an ego density of 1,000 points per square meter. It looks like a solid block of color on my screen. But if 995 of those points hit the blades of grass and only 5 points manage to find a gap and hit the actual dirt, my useful ground density is terrible.
And this is where we have to look at how ground classification algorithms actually function. Most software uses something like a progressive morphological filter or a cloth simulation filter.
A cloth simulation filter, how does that work?
In a cloth simulation, the algorithm flips the point cloud upside down mathematically and simulates dropping a rigid cloth over the points.
Oh, that's clever. So the highest points are actually the deepest ground points.
Exactly. The cloth rests on those highest points, but if your useful ground density is too low, the gap between those dirt points is too wide.
So the cloth just sags.
It sags, or it rests on the bottom layer of the thick grass instead of the dirt. The algorithm thinks the grass is the ground. For a true terrain model, you must design a flight plan that forces enough light through that vegetation to provide solid point support on slope breaks, embankments, and ditch bottoms.
Otherwise, the ditch just disappears.
Yep. If your ground points are sparse, the algorithm will just draw a flat triangle across the ditch, effectively erasing it from the final model.
Let's pivot to corridor mapping. Things like highways, railway lines, and long pipeline routes. The sources indicate the mathematical priority completely shifts here. It's less about raw local density and more about longitudinal consistency.
Corridor mapping is structurally unforgiving. When you map a 20-mile highway corridor, the route is going to expose every single weakness in your methodology.
Because it's so long.
Right. The client is expecting a continuous ribbon of reality that is uniformly stable from mile marker 1 to mile marker 20. Think about the edge matching required here. You are flying long, linear strips.
Over and over.
Yeah. If your line spacing works perfectly over the flat sections of the highway, but fails to maintain proper overlap when the highway dips into a steep valley, the geometric tie points between your flight lines degrade.
So the data looks good and then suddenly looks bad.
Exactly. The surface will look incredibly rich and detailed, and then suddenly look patchy, soft, or misaligned, and then rich again. When the client software tries to calculate the exact slope of the asphalt for water runoff, that inconsistency destroys the integrity of the calculation.
For corridors, consistency across distance is the governing metric. But what happens when the target isn't the ground at all? Utility work, like inspecting transmission lines, is a massive sector for LiDAR, and the target is a half-inch cable hanging 100 feet in the air.
Utility inspection forces operators to abandon everything they know about traditional mapping.
Really? Everything.
Pretty much. Average density across a project site is a completely meaningless metric here. The client does not care how beautifully you modeled the access road or the grass 100 feet away from the transmission tower.
They just want the tower and the wires.
Their entire focus is on target density, on narrow, vertical, and partially obscured assets. They need to see the exact structural geometry of the lattice tower, the orientation of the crossarms, and the mathematically precise sag of the conductor cables under different thermal loads.
Which introduces the physics of beam divergence, right? If the laser beam gets wider, the further it travels, hitting a tiny cable becomes a statistical challenge.
Exactly. As the pulse of light leaves the sensor, it spreads out, kind of like a flashlight beam.
Right. The further away you shine it, the wider the circle of light.
Yes. By the time it is 200 feet away, the footprint of that single pulse might be several inches wide. If that wide footprint hits a half-inch cable, only a tiny fraction of the light energy reflects back to the sensor. The rest continues past the cable.
So it just completely misses most of the energy.
Right. This is why you cannot just rely on high PRR from a high altitude. You have to physically position the drone to maximize the amount of light energy returning from that tiny reflective surface.
Which means flying differently.
That demands repeated looks, highly overlapping passes, and specific flight line orientations that ensure the critical assets are captured in the strongest part of the laser's field of view, not relegated to the noisy edges.
And then there's forestry, which the text beautifully describes as the vertical complexity problem. Total density lies to you in a forest. Vertical structure tells the truth.
Forestry takes a relatively straightforward two-dimensional coverage problem and turns it into a chaotic 3D layered probability problem.
Probability, how so?
Every single laser pulse you fire downward is entering an obstacle course. You can think of it in terms of light attenuation. Some pulses hit the top of the canopy and reflect entirely. Some pulses hit the edge of a leaf, splitting the energy, where part of the light returns as a first return, and the rest continues downward to hit a branch, creating a second return.
And you just hope some of it makes it to the ground.
Exactly. Some pulses find microgaps and travel all the way to the forest floor. If your client is a timber company needing a bare earth model to design logging roads, and you fly the drone high and fast to cover the acreage quickly, you will generate a stunning, dense model of the treetops.
But the ground gets nothing.
Your ground class will starve.
You essentially have to design the flight geometry to punch enough light through the canopy to paint the floor. You're basically playing the odds.
Yes.
Yep.
You are actively managing statistical probability. You have to fly significantly slower and increase your overlap massively, simply to generate enough total pulses from enough different angles that a sufficient percentage survives the journey through the branches to strike the dirt.
Before we move off deliverables, let's talk about stockpiles. Gravel pits, mining operations, construction sites doing cut and fill. The sources say ego density is entirely useless here.
Because the client is purchasing one very specific mathematical output, a believable volume calculation.
It's just a volume number.
Right. They do not need 2,000 points per square meter on the flat, boring top of the gravel pile. They need absolute surface continuity on the critical break lines.
The edges, essentially.
The crest of the pile, the steep flanks, and the toe, the exact line where the pile meets the natural ground. Volume is typically calculated using trapezoidal prisms derived from the TIN surface.
So what happens if you don't have enough points on those edges?
If your point cloud is thin on the crest of the pile, the software's interpolation will literally cut the corner. It will round off the top of the pile.
Well, that sounds bad for volume.
It is. When that happens, your volume calculation instantly loses thousands of cubic yards of material. In mining, that missing volume represents real, tangible revenue loss to bad flight geometry.
Reviewing all these different deliverables, from ground filtering to utility cables to volume calculations, brings us to a concept in the sources that I find incredibly useful: the measurement budget. We're used to thinking about battery budgets, right? I have 30 minutes of a flight time, but this is different. How does an operator spend their measurement budget?
Think of your LiDAR sensor as an engine that produces a finite amount of observation effort per second. That effort is your budget. Spreading it thinly and evenly over a massive area dilutes its structural value.
So you have to be intentional.
Very intentional. If you are flying a high-stakes engineering support survey where a civil engineering firm is going to base grading decisions and concrete quantity takeoffs on your data, You need to allocate a massive confidence budget.
Because mistakes are expensive.
Exactly. You cannot afford the software creating weird edge-matching artifacts because those artifacts will literally be poured into concrete downstream. So you spend your sensor's effort intentionally, you fly lower to decrease the beam footprint, you fly slower to compress the along track spacing, you tighten your flight lines to increase redundant overlap.
You sacrifice speed for quality.
You knowingly sacrifice the total acreage you can map in a single day in order to buy structural mathematical integrity for the acres you do map.
Which perfectly transitions us into the actual execution. We know what the deliverable is. We know how we want to spend our measurement budget. Now we actually have to manipulate the aircraft in the sky to capture it.
This is where it gets highly technical.
Yeah, the sources refer to this as the connected system of geometry. It's a mechanical chain reaction where turning one dial secretly alters the physics of everything else. And they give us a really simple mnemonic to track the four main levers: LOSD, lines, overlap, speed, density.
The physics of LOSD are where mission planning becomes an absolute art form. It is a closed-loop system of compromises.
Let's start with altitude and swath width, which heavily dictates the density piece. I really like the paint roller analogy for this from the sources.
It's a great way to visualize it.
Yeah, imagine the laser scanning rapidly back and forth beneath the drone is like a paint roller. If you raise your altitude from 200 feet to 400 feet, your field of view projects wider onto the ground. You're essentially swapping out a standard paint roller for a much wider one.
And you can cover more ground.
Right. You can cover a wider swath of the site with every pass, which feels incredibly efficient. But the volume of paint, the number of laser pulses per second, hasn't changed, so the paint goes on much thinner. Your density drops.
But there's a much more insidious problem the sources highlight here. The difference between your theoretical swath and your usable swath.
The paint roller analogy is excellent, but we need to add the mechanism of incidence angle to fully understand the danger of a wide swath. When the LiDAR scanner is pointing straight down at nadir, the laser pulse hits the ground at a perpendicular angle.
Straight down.
Exactly. The footprint is tight, the energy is concentrated, and a very strong signal bounces directly back to the receiver. But as the scanner's mirror sweeps out to the far left and right edges of its field of view, the physics change. The laser is now hitting the ground at an oblique angle.
Like shining a flashlight straight down at the floor versus shining it across the room at the wall.
Yes.
The nice, tight circle of light stretches out into this long, dim, smeared oval.
Exactly. That oblique angle physically elongates the laser footprint on the ground. The laser's energy is smeared over a larger area, which means the amount of photons bouncing back to the sensor is drastically reduced.
The signal-to-noise ratio drops.
Furthermore, that oblique angle is highly susceptible to occlusion. A tree at the edge of your swath will cast a massive data shadow outwards, hiding the ground behind it.
Oh, I see.
That is why the far edges of your theoretical swath are the weakest, least trustworthy parts of your entire dataset. Agencies like the USGS and NOAA, which write the gold standard specifications for spatial data, do not even evaluate density across the whole raw swath.
They just throw the edges out.
Basically, they trim the edges off mathematically and only evaluate the usable center portion, typically the inner 90 to 95% of the scan.
So if an operator plans their flight lines, assuming they can use 100% of the swath width just to save time, they are intentionally building their final map out of the noisiest, weakest, most shadow-prone data the sensor can produce.
They are structurally compromising the data before the drone even takes off. Which brings us directly into the first letter of our LOSD acronym: lines, the orientation, spacing, and geometry of your flight lines.
The text notes that parallel lines aren't a default religion, which is funny because literally every automated drone mapping app on the market defaults to a simple lawnmower pattern of parallel lines.
You draw a box, it draws parallel lines, you hit go.
Exactly. But it is the default because it is computationally easy for an app to generate, not because it is mathematically superior. Let's return to the River Valley Corridor example.
Okay.
If you are mapping a winding valley and you just blindly command the software to fly a parallel lawnmower pattern across it, you are going to encounter areas where the drone is flying perpendicular to the steepest slopes.
Oh, so you're hitting it from the worst possible angle.
You are exposing the weakest oblique edges of your laser swath to the hardest, most extreme terrain. Advanced operators break the mission up. They align flight lines with the contours of the terrain to maintain consistent incidence angles.
That makes a lot of sense.
And more importantly, professional LiDAR geometry utilizes cross lines.
I've seen these on flight plans. You fly your main parallel lines north to south, and then you fly a line or two east to west, perpendicular to the main block. But if they aren't about adding density, what is their actual mechanical purpose?
Cross lines are the rigid mathematical skeleton of a project. They're not there for coverage, they are there for calibration and QA/QC.
Calibration, like fixing errors.
Remember the IMU drift we discussed earlier? Even the most expensive IMU accumulates microscopic errors in its pitch, roll, and yaw calculations over time. A crossline provides a perpendicular dataset that physically intersects every single one of your main flight lines.
An intersection.
Right. If your main north-south line calculates a patch of bare concrete at an elevation of 100.0 feet, and the east-west cross line passes over that exact same patch of concrete 10 minutes later and calculates the elevation at 100.4 feet, you instantly know your system has experienced trajectory drift.
Because it's the exact same spot.
Exactly. The software uses the cross lines as rigid tie points to run a bore sight calibration adjustment, mathematically locking the main lines back into their true spatial position.
Which leads us perfectly into overlap, the O in LOSD. The sources are absolutely adamant that overlap is not just about making sure you didn't miss a spot. It is the trust architecture of the entire point cloud.
Trust architecture is the perfect term. A lot of operators transition into LiDAR from drone photogrammetry.
And they're totally different, right?
Completely. In photogrammetry, you need massive overlap, like 80%, just so the software can find matching pixels to stitch the photos together.
The photos need to overlap to stitch.
But LiDAR doesn't stitch. Every point is an independent, mathematically absolute coordinate. In LiDAR, overlap is how the dataset proves itself to itself. It provides structural redundancy.
What does a failure of overlap actually look like in the final data? If I get it wrong, what do I see?
If your line spacing is too wide, your overlap is weak. This forces the software to use the far left noisy edge of strip A and overlay it with the far right noisy edge of strip B.
Those noisy edges we talked about earlier.
Exactly. Because both edges are oblique, weak, and prone to trajectory errors, they rarely align perfectly. In the 3D point cloud, this misalignment manifests as what the sources call subtle scars, or soft edges.
A subtle scar.
A perfectly flat parking lot will suddenly have a 2-inch vertical step right in the middle of it.
And when you hand a parking lot with a phantom 2-inch step to a classification algorithm,
the algorithm loses its mind. It looks at the local elevation variance, sees a sudden vertical step, and assumes it has found a physical feature, a curb, a retaining wall, or a berm.
and it classifies it incorrectly.
Incorrectly. The weak overlap created a geometric scar, which triggered a classification failure, which ultimately results in a flawed engineering model.
Let's hit the S in LOSD, speed. The sources highlight excessive speed as the classic beginner's mistake.
Oh, everybody wants to fly fast.
Because flying fast feels incredibly productive. You are covering acres per minute, you are beating the battery life, you're getting the job done before lunch. But let's look at the mathematical consequence of speed on the data structure.
We touched on this earlier regarding PRR, but we need to look at the mechanism of the scanner itself. Most drone LiDAR systems use a rotating mirror or a prism to sweep the laser beam side to side across the swath.
Back and forth.
Back and forth. That mirror rotates at a fixed mechanical rate, say 100 times per second. If the drone is flying at a slow 5 meters per second, the physical distance the drone travels forward between each sweep of the mirror is very tight. The scan lines are packed closely together.
Going back to the paint roller, it's moving forward slowly so the coverage is thick and uniform.
Exactly. But if you accelerate the drone to 15 meters per second to cover more ground, the mirror is still only spinning 100 times per second.
So the drone moves further between each sweep.
Yes. The physical distance the drone travels forward between each sweep has now tripled. The scan lines stretch out. You get massive along-track point spacing. Your data is beautifully dense, side to side, across the swath, but violently stretched front to back.
Like a slinky being pulled apart.
That's a great visual. You lose local support for small features. If there is a small utility vault or a narrow ditch running perpendicular to your flight path, a fast drone might step right over it.
Just skip over it completely.
It drops a scan line right before it and right after it, missing the feature entirely.
And once again, that forces the processor to guess what exists in that stretched out gap. This really highlights the domino effect the sources warned about. Changing one setting cascades through the entire system.
The cascade is relentless. Let's map out a very common real-world scenario. An operator arrives on site and realizes a storm is rolling in.
Oh, classic time crunch.
Right. They want to get the job done faster. So their first decision is to raise the flight altitude.
Because raising the altitude widens the theoretical swath. You can cover more ground.
Correct. And because they believe that theoretical swath is entirely usable, they go into their flight planning app and significantly widen the spacing between their flight lines.
Which means they fly fewer total passes.
Exactly.
But because they widen the spacing based on the theoretical swath, their actual usable overlap drops to almost nothing. The rigid trust architecture is gone. They are now relying exclusively on those noisy, oblique edges to tie the model together.
And to guarantee they beat the rain, what do they do next? They increase the drone's flight speed to maximum.
So the long track scan lines stretch out, tearing gaps in the local density.
The result is a total collapse of the structural geometry. You have weak edges, zero redundancy for IMU calibration, and stretched out point spacing that fails to capture microtopography.
And when the processor receives that data back in the office,
The filtering algorithms fail. The software cannot differentiate between a low-lying shrub and a mound of dirt because the point density is too sparse to mathematically define the shapes.
the software is just guessing at that point.
The operators save 20 minutes in the field, but they just bought the data processor 3 days of agonizing manual cleanup work in the office.
Oh.
And even after manual cleanup, the final deliverable will still lack the underlying structural integrity the client paid for.
Saved 20 minutes in the field, bought 3 days of manual cleanup. That is the harsh reality of LiDAR physics. But here's the catch. The LOSD settings, lines, overlap, speed, and density, they can be mathematically perfected on a flat spreadsheet in the office.
But we don't fly in spreadsheets.
No, we do not. Which brings us to the environmental factors. The real world is messy. Complex terrain and thick vegetation will completely overwrite your perfectly planned LOSD rules mid-flight.
If we bring this back to the core theme of identity, a pilot assumes they are flying a constant altitude above sea level and expects the ground to behave beneath them.
Right.
An operator understands that the terrain is an active, dynamic participant in the mission's geometry.
Let's visualize rolling terrain. Say I program my drone to take off and fly a grid at 300 feet above ground level AGL based on the elevation of my launch pad. I start flying, and midway through the grid, the drone crosses over a deep river valley. Suddenly, my drone isn't 300 feet above the ground anymore. It's 500 feet above the ground at the bottom of the valley.
And we know exactly how the physics cascade from an increase in altitude.
The wide paint roller again.
Right. As the effective AGL increases to 500 feet, the laser's field of view projects wider, the swath widens, the laser footprint enlarges, the photon energy dissipates over a larger area, and your useful density plummets right at the bottom of the valley.
And the bottom of the valley is usually where the civil engineer needs the most accurate drainage data.
Exactly. Your overlap geometry falls apart.
Wow.
Conversely, if your flight path takes you over a sudden ridge or a hill, your effective height above ground might drop from 300 feet to 100 feet.
So the swath narrows drastically.
Dramatically. And if you didn't plan your line spacing to account for that ridge, the narrow swaths might not touch.
Oh.
Your overlap drops to zero. You return to the office with a literal, unmapped gap in the physical center of your data.
A flat paved site forgives lazy planning. Complex terrain will instantly ruthlessly expose it.
Which is why advanced operators utilize terrain following software, where the drone adjusts its altitude dynamically based on a coarse digital elevation model, ensuring the LOSD geometry remains mathematically constant regardless of the topography beneath it.
And then there is the ultimate enemy of LiDAR, vegetation. The sources refer to vegetation as an obstacle field. It takes the math we've been talking about and just scrambles it.
It really does. Imagine you rigorously test your LOSD settings over a golf course fairway. You dial in the speed and overlap, and you get a stunning, tight, accurate point cloud.
Looks perfect.
Then you take those exact same settings and fly over a dense, deciduous forest. The canopy acts as an optical umbrella. Millions of your laser pulses are immediately absorbed by the chlorophyll or scattered by the leaves.
Only a tiny fraction makes it through.
A statistically minor fraction. They find a micro gap in the leaves, travel down, and hit the actual Earth. A flight plan that yields perfect structural density over short grass will completely, utterly starve the ground class when forced to penetrate a canopy.
But it's not just the giant, obvious trees that cause issues, is it? The text points out the unique sneakiness of brush. Scrub brush, palmettos, tall, thick weeds. Why is low brush harder for the software to figure out than a 100-foot pine tree.
It comes back to the mechanics of the classification algorithms. With a tall pine tree, there is a massive, clear vertical separation between the points hitting the canopy and the points hitting the dirt.
A big gap.
A huge gap. The algorithm looks at the data, sees a cluster of points 80 feet in the air, sees a void, and sees a cluster of points at 0 feet. It can easily say 80 feet is vegetation, 0 feet is ground.
Makes sense.
But low brush destroys that vertical separation.
Right, because the points are returning from a chaotic mix of 1 foot, 2 feet, and 6 inches off the ground. It's all blended together in a dense mat of noise.
Exactly. The algorithm analyzes the local area, looking for smooth elevation continuity to define the bare earth. But when it looks at low brush, it sees a massive variance in elevation over a very small distance.
So it gets confused.
Because there is no clear separation between the bottom of the brush and the soil, the algorithm often gets tricked into thinking the bumpy top of the brush is a rough, physical ground surface.
So how do you beat that?
To defeat brush, an operator has to rely on brute force geometry. They must significantly increase their line overlap and drop their flight speed to compress the scan lines.
Just hammering it with lasers.
Mathematically forcing a higher volume of laser pulses into the tiny gaps in the scrub, ensuring enough pulses hit the hard dirt to give the algorithm an undeniable baseline to lock onto.
And beyond vegetation, you have to factor in transient environmental conditions. The world changes day to day, and that alters how light behaves.
This variable constantly catches pilots off guard. Say it rained heavily the night before your flight. Puddles of water on the ground act as specular reflectors for the near-infrared wavelength typically used by LiDAR.
Which is around 164 nanometers, right?
Usually, yes. The water absorbs or bounces the light away from the sensor, resulting in 0 returns.
So you just get black holes in your data.
Exactly. Fog, high humidity, or smoke scatters the laser pulses in the air, raising the noise floor and creating phantom points in the sky. And phenology, the seasonal state of the leaves, is a massive factor.
Summer versus winter.
A leaf-on flight in July requires completely different LOSD geometry than a leaf-off flight in January over the exact same forest. A plan that worked perfectly on Tuesday might fail spectacularly on Thursday simply because of a shift in the environmental envelope.
We've talked a lot about filtering the ground, but what if the target is small and isolated? The text brings in the NOAA obstruction survey guidance to address this. If I'm mapping an airport approach path and I need to guarantee I capture a thin radio antenna or a low reflectance obstruction, can I just crank up the PRR to maximum and rely on the sensor's raw power?
No, and the NOAA standards are explicit about this. For small, subtle, or low-contrast targets, you cannot rely on PRR from a high altitude. You must address the physical physics of the beam divergence we discussed earlier.
The flashlight beam spreading out.
Right. The NOAA guidance dictates narrow beam divergence and lower flying heights.
Because physically flying the sensor closer to the antenna shrinks the diameter of the laser footprint before it impacts the target.
Correct. By flying lower, the footprint might only be an inch wide when it hits the antenna rather than 4 inches wide. This concentrates the photon energy, ensuring a much stronger, undeniable return signal back to the receiver.
You have to physically position the sensor to win the physics equation.
You cannot outcompute bad physics in the office.
Okay, let's take a breath and recap where we are. We have discussed engineering the evidence mathematically. We have defined the specific deliverable. We have meticulously balanced the connected system of LOSD geometry. We have battled the physical enemies of terrain and brush. And we have positioned the sensor perfectly to defeat beam divergence.
A lot of math.
We have, in theory, engineered the perfect digital evidence. But, well, the physical drone doesn't care that the LiDAR payload hanging underneath it cost $100,000. It still have to obey the law.
And this brings us out of the mathematical envelope and into the regulatory envelope.
Legal stuff.
Because while you have adopted the mindset of a data operator, you are, legally speaking, still an aircraft pilot operating a vehicle in the National Airspace System.
The sources are incredibly blunt about this. A fancy sensor and a critical infrastructure contract do not exempt the operator from airspace rules, night operation restrictions, or visual line-of-sight laws.
You are operating inside a strict, unyielding legal box.
And the thickest wall of that box is VLOS, visual line of sight.
VLOS is where the temptation for operators to stretch the rules is strongest, particularly in linear corridor mapping. The legal standard in both the United States and Canada is unforgiving.
Spec is not sight.
Yes, the sources provide a phrase that I believe should be painted on the wall of every commercial drone operations center. Spec is not sight.
Let's build a real-world narrative around that phrase because it highlights how easily operators rationalize breaking the law. Let's say you are mapping a 2-mile section of transmission lines. The client needs the data tomorrow. You stand at one end of the corridor, launch the drone, and fly it a mile away down the wires.
A mile away is very far.
It is. You look up, and against a gray, cloudy sky, you can just barely see a tiny white pixel hovering in the distance. To a pilot under pressure, they point at that pixel and say, I have line of sight. I can see it. It's a speck, but I see it.
But from a regulatory and safety standpoint, seeing a tiny dot does not meet the legal standard of visual line of sight. Consider the actual mechanics of deconfliction.
Deconfliction.
Avoiding other aircraft. The law, whether under Part 107 in the U.S. or CARS Part 9X in Canada, requires the pilot to know the aircraft's attitude, its altitude, its direction of flight, and they must be able to effectively scan the surrounding airspace for conflicting air traffic.
Right.
If your drone is just a white speck a mile away and a crop duster suddenly crests the tree line heading toward it, you cannot determine if your drone is banking left or banking right. You do not know its attitude.
So you can't dodge.
Therefore, you cannot execute a reliable evasive maneuver. You are not flying VLOS. You are flying blind, staring at a pixel, and simply hoping the sky remains empty.
The immediate pushback I hear from operators in that scenario is, fine, I can't see it clearly, but I brought my buddy with me. I'll just use a visual observer. I'll hand him a radio, put him a mile down the road in a lawn chair, and he can watch the drone for me. Problem solved.
The sources specifically call that out as the visual observer myth. A VO is a safety enhancement. The text brilliantly compares a VO to a seatbelt in a car.
A
seatbelt makes driving safer, but wearing a seatbelt doesn't legally allow you to drive on the sidewalk. A VO is not a legal teleportation device to bypass VLOS laws.
Oh, that's a great way to put it.
Under standard baseline rules, the pilot in command manipulating the controls still needs to possess the capability to see the aircraft as required. If the PIC loses that capability, relying entirely on a VO down the road means the operation has shifted outside the baseline regulations.
Which requires a waiver.
Yes, specific waivers or complex operational certificates.
Let's dig deeper into the specific U.S. regulations under FAA Part 107. Because the technology is evolving faster than people's understanding of the law, we have to talk about remote ID.
Remote ID is now the foundational law of the land in the U.S. You can think of it as a digital license plate for your aircraft.
How does it work?
It uses Bluetooth or Wi-Fi to constantly broadcast the drone's unique identity, its 3D location, its velocity, and crucially, the exact geographic location of the pilot's control station.
And operators hate it. I see complaints online constantly where an operator says, I'm mapping critical power grid infrastructure. This is sensitive data. I don't want to broadcast my control station location to everyone with a smartphone app. I'm just going to turn remote ID off.
Which immediately invalidates the legality of their flight. The FAA considers remote ID the absolute cornerstone for integrating unmanned aircraft into the national airspace safely.
So it's not optional.
If your commercial drone requires registration, it requires active remote ID compliance. You cannot simply disable your digital license plate because you feel your mission is sensitive unless you are operating under very specific, rare federal security exemptions.
Let's tackle another massive myth under Part 107. The moving truck maneuver.
Oh, I see this all the time.
I see this done constantly on YouTube. An operator has a 10-mile roadside mapping contract. To maintain that visual line of sight we just talked about, they sit in the bed of a pickup truck with the controller, staring at the screen, while their partner drives the truck slowly down the highway, pacing the drone exactly.
Sounds efficient.
It maintains VLOS, it covers ground incredibly efficiently, and it avoids packing up the gear 10 times a day.
It feels like an elegant, efficient solution, and it is explicitly a violation of standard Part 107 rules in almost all commercial scenarios.
Why is that?
The FAA rule regarding operations from moving vehicles is highly restrictive. It generally prohibits operating a small UAS from a moving land or waterborne vehicle unless two strict conditions are met.
What are they?
You must be operating over a sparsely populated area, and you cannot be transporting another person's property for compensation or hire. The moment you are executing a commercial LiDAR mapping contract for a municipal client from the bed of a moving truck on a populated roadway, you have breached the regulatory envelope.
Wow.
What operators call mobile efficiency, the FAA calls a compliance violation.
Now let's look north to Canada because the regulatory landscape there just underwent a massive systemic shift. The sources spend a lot of time highlighting the 2025 reforms, specifically the SOR 2025-70 framework under the Canadian Aviation Regulations, or CARS.
Canada's approach to integrating advanced operations is fascinating and heavily structured. Prior to these 2025 reforms, if an operator wanted to push beyond standard visual line of sight, say, to map a massive forestry tract, they often had to apply for a Special Flight Operations Certificate, an SFOC.
Was that hard to get?
It was treated essentially as a one-off waiver. It was restrictive, slow to process, and limited industry growth. The 2025 reforms fundamentally changed the architecture. They opened up formalized regulatory pathways for much more complex operations, specifically extended visual line of sight, or EVLS, and true beyond visual line of sight, BVLOS.
So to summarize, the Canadian government made it easier for operators to fly further.
No, and that is the critical, dangerous misunderstanding many operators have. The sources phrase this dynamic perfectly. Canada didn't just open the door to complex flights, they built more hallways with more checkpoints.
Always in checkpoints.
They created structured legal pathways, but those pathways require rigorous compliance. Operating under these new rules requires entirely new operator certificates. It requires drones with specific approved technical hardware capabilities.
The whole system.
It requires exhaustive procedural manuals dictating emergency responses based on the kinetic energy of the drone and its exact proximity to people on the ground.
Wow.
And perhaps most importantly, in Canada, under these rules, a site survey is not just a best practice chapter in a textbook. It is a mandatory, auditable regulatory requirement. Before the operator even powers on the aircraft, they must formally, documentedly determine that the operational volume is suitable and safe.
Let me interject with a scenario that I think represents the ultimate real-world dilemma for an operator listening to this. Let's say my mission plan is mathematically flawless. I have tuned the LOSD geometry perfectly. I've utilized cross lines for IMU calibration. I have accounted for the beam divergence and the terrain. I am building a highly accurate terrain model for a critical flood mitigation project. The data matters.
Okay, setting the stage.
But out in the field, I realize there is a thick stand of pine trees blocking my visual line of sight to the final 500 feet of the river corridor. If I do the legal thing, land the drone, pack the equipment into the truck, drive 20 minutes to the other side of the tree line, unpack, and launch again, I'm going to lose the last hour of daylight.
A very common situation.
I will fail to deliver the data to the engineers tomorrow morning. Can't I just stretch the VLOS rules just a tiny bit, just for 2 minutes, to capture those last 500 feet and get the client the exact mathematical data they desperately need?
The answer is unequivocally no. And the reasoning goes back to the difference between a pilot and an operator. Easier is not a legal standard.
Easier is not a legal standard.
If your operational concept pushes you outside the legal VLOS box, you do not pretend a weak visual chain solves it. You do not look at a spec and pretend you have attitude awareness. You do not hope a VO down the road makes it legal.
So what are your choices?
You have two professional choices. You break the mission into smaller, compliant segments and accept the operational delay, or you do the rigorous, months-long administrative work ahead of time to secure the proper waivers, authorizations, or complex operator certificates.
Because if the foundation of the flight is illegal, the mathematical integrity of the data is poisoned by the legal vulnerability.
Exactly. The text stated earlier that the processor inherits your ethics regarding data structure. Well, the legal framework inherits your professionalism. A legally compromised flight invalidates the professionalism of the entire operation.
How so?
Think about the cascading consequences. If you deliver that floodplain data and the civil engineering firm uses it to design a multi-million-dollar levee, and a year later there's a catastrophic flood and a lawsuit.
Oh boy.
During discovery, if it is revealed that the foundational flight capturing the data was conducted illegally, outside of regulatory compliance, the entire data set, the engineered evidence you worked so hard to build, might be thrown out of court entirely. The most mathematically perfect point cloud in the world is useless if the method of collection breaks the law.
Wow. Okay. That is a sobering reality check. And it brings us to the end of our journey today. We have covered a massive amount of technical and regulatory ground.
We really have.
We started by dismantling the myth of ego density, the beginner's belief that a giant 2 billion point file is automatically good data. We unpack the physics of IMU trajectory and how interpolation works.
The garden hose versus the fire hose.
Exactly. We learned that the true product is the structural strength of the evidence, and that we must always plan backwards from the specific mathematical needs of the client's deliverable, whether that's a ground-classified TIN, a consistent highway corridor, a high-density utility wire, or a volumetric stockpile calculation.
From there, we walk through the connected mechanical system of LOSD: lines, overlap, speed, and density.
The domino effect.
We traced the physical cascade of choices, how raising your altitude widens your beam footprint and forces oblique incidence angles, which tempts you to widen your line spacing, which completely destroys the trust architecture of your overlap, which leaves your data relying on weak, noisy edge points.
And if you add too much speed to that equation, you stretch your scan lines to the breaking point, tearing structural holes in the microtopography.
We discussed the physical enemies of geometry, how the dynamic terrain of a river valley alters your effective altitude and wrecks your swath width.
And vegetation.
We looked at the algorithms and how the chaotic, noise-inducing structure of low brush can completely trick the software into starving your bare earth model if you don't adjust your flight speed to force enough light to the dirt.
And finally, we grounded all of this precision engineering in the strict legal realities of the airspace. We dispelled the visual observer myth, broke down the illegality of the moving truck maneuver under Part 107, and reinforced the life-saving concept that spec is not sight.
A vital lesson.
Whether you are operating under FAA rules in the U.S. or navigating the structured pathways of the new 2025 RPAS reforms in Canada, the cost of your payload does not exempt your aircraft from the law.
So the ultimate golden rule for the spatial data professional, derived from everything we've synthesized today: don't look at the drone and ask, how much area can I cover with this battery?
Instead, ask what?
Look at the project and ask, what mathematical structure does this client need to believe me when they zoom in on the hardest, ugliest, most heavily vegetated part of the site?
Shifting that one question changes your entire operational methodology.
It redefines the industry entirely.
It really does. And I want to leave you, the listener, with a final provocative thought based on the concept of engineered evidence. As we've discussed, the software processor ultimately inherits the structural honesty of the choices you made in the field.
The processor inherits your ethics.
Yes, the decision to widen a line spacing, to save 5 minutes of walking, or to fly just a little too fast to beat a rainstorm dictates whether the final 3D map is a true, measured reflection of reality, or just a highly sophisticated, mathematically smooth guess.
Which is a huge responsibility.
It is. Which forces us to wonder, as our society becomes increasingly reliant on digital twins. The flood risk maps that determine insurance rates, the autonomous vehicle highway models, the power grid clearance analytics. How much of the digital world we stake our lives on every single day is based on true engineered observation? And how much of it is just an algorithm trying its absolute hardest to cover up a pilot's rush to get home?
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.